Let's now take a few minutes to talk about electromagnetic waves. Now, what do you know about electromagnetic waves? Well, everything that we do, including the video that I'm doing, is made possible because of electromagnetic waves. Light is a form of electromagnetic waves. Well, let's talk a bit about that. A changing magnetic field produces an electric field. Is that right? It is a fluctuating magnetic field that generates an electric current. So a changing magnetic field produces an electric field, and a changing electric field produces a magnetic field. I have told you this even before, that I have misspelled fields several places, so ignore that. Now, the magnetic and electric fields are perpendicular to each other. If the electric field is propagated in the horizontal direction, magnetic field will be propagated in the vertical direction. And both these fields are actually alternating. That's in the form of transverse wave. The net result of such interacting, changing fields is the propagation of orthogonal electric and magnetic fields in space. Now, what's the meaning of orthogonal electric and magnetic fields? Well, orthogonal, of course, means perpendicular. That means if the magnetic fields is propagated horizontally, the electric field is propagated vertically. These two fields are perpendicular to each other. Now, this phenomenon is referred to as electromagnetic waves. So what is the phenomenon of electromagnetic waves? Electromagnetic waves are simply propagation of electric and magnetic fields which are at right angles to each other. Now, electromagnetic waves are transverse wave whose wavelength lambda is measured from crest to crest, that is from maximum of electric or magnetic displacement. You are familiar with transverse waves. So when you talk about the maximum of the wave, it could be the maximum displacement for electric or magnetic fields. Now here I have an illustration of that. The magnetic field, if this is the magnetic field, that is the electric field. So the magnetic field is the horizontal vibration and the electric field is the vertical vibration. And look at the direction of propagation. The direction of propagation is at right angles to both these. So if this is the magnetic field, suppose we call this x direction, and the electric field is in the z direction, then the direction of propagation is the y direction. Is that right? If this is x and this is z and this will be y, you can actually orient it in any way you want. The most important thing is the magnetic fields, the electric field, and the direction of propagation are mutually perpendicular to each other. I have another diagram here. Here, this is the magnetic field. The blue line, well, that is a horizontal wave, and the red wave is the electric field, which is vertical, and the direction of propagation is at right angles to both these. The magnitudes of E and B are in phase. What does that mean? The magnitudes of B and E are in phase. When the magnetic field reaches a maximum, the electric field also reaches a maximum. When the electric field is zero, the magnetic field also is zero. So the electric and magnetic fields are in phase, and look at the equation that they are related by. They are related by E equal to CB. Electric field equal to C times B, where C is the speed of electromagnetic waves in space. Where C is the speed of electromagnetic waves in free space and can be expressed in terms of Now I want you to pay attention to this and appreciate this very important and interesting concept. C is the speed of electromagnetic waves in free space. Epsilon naught is the permittivity of free space, and mu zero is the permeability of free space. You can see here electric property, magnetic property, electromagnetic property. So C is the speed of electromagnetic waves, and this speed can be expressed in terms of this epsilon naught and mu zero, like this. C equal to 1 over square root of mu zero times epsilon naught. Now, isn't that interesting? If you know the values of mu zero and epsilon naught, which you know, alright, how many of you can tell me what is mu zero? Well, mu zero is 4 pi times 10 to the negative 7. Epsilon naught is 8.85 times 10 to the negative 12. Well, all forms of electromagnetic waves travel in free space with the same speed c. Now, how many forms of electromagnetic waves do you know? Well, we've got radio waves, infrared, visible light, the lights that we see, ultraviolet, X-rays, gamma rays. They are all electromagnetic waves, and they all travel in space with the same speed c, and the value of c can be computed from the values of mu zero and epsilon naught. Replace mu zero by 4 pi times 10 to the negative 7 Tesla meter per ampere, and epsilon naught, the permittivity of free space, 8.85 times 10 to the negative 12 Coulomb squared Newton per meter squared, and that gives you c equal to 3 times 10 to the power of 8 meter per second. Now, this is an important constant, and according to Einstein, nothing can travel faster than this, right? Okay. How about electromagnetic spectrum? Electromagnetic spectrum is actually a collection of all forms of electromagnetic waves. Now, I think in the discussion on thermodynamics, we talked about the radiation that are emitted by all objects. All objects at all temperature emits radiation in the form of electromagnetic waves. Now, electromagnetic spectrum, radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays, are all electromagnetic waves of different wavelength and frequencies. Now, all these range of waves or radiations put together is called electromagnetic spectrum. The wavelengths of these radiations vary from about 1 kilometer for radio waves, radio waves themselves range from few kilometers to few millimeters, short waves and long wave radio. Now, so vary from about 1 kilometer for radio waves and a few picometers for very high energy gamma radiation. These gamma radiations are so short they can actually penetrate through you without even knowing. Now, the speed of electromagnetic waves can be expressed in terms of their frequency and wavelength. Well, all forms of waves are described by this equation, C equal to F lambda. So we got actually two equations for speed of electromagnetic waves. One in terms of mu zero and epsilon naught, the other in terms of the frequency and wavelength. Now, here is a rough picture of electromagnetic spectrum. If you start from the left, you got radio waves of wavelength few kilometers, and you go to the right, the wavelength is steadily decreasing, and you come to microwaves. Well, all these are radio waves, long radio waves to short radio waves. Then you have a range of microwaves, you have radars, infrared, which are heat rays. So the wavelength is steadily decreasing. And look at the visible light. Visible light is a very small part of the electromagnetic spectrum. And how many different types of waves are in the visible region of that? It's over 3,000 different waves. Well, then comes to ultraviolet. We got X-rays, gamma rays, and so on. So the wavelength ranges from, say, 10 to the power of 3 meters to about 10 to the power of -12. That's the one I talked about, a picometer. Now, the frequency of radio waves, say, is about 10 to the power of 6. Now, as the wavelength decreases, the frequency will increase. And the energy, well, a radiation carries energy. The electromagnetic radiations can be considered to be particle in nature, and we call those particles photons, and the energy of the photons are also listed there. The energy steadily increases as the frequency increases. You can see the energy is given in electron volt. An electron volt is the energy acquired by an electron when it is accelerated by just 1 volt. So you can see the energy of a radio wave photon is 10 to the -9 electron volt, 1 billionth of an electron volt, very small energy. While the energy of a gamma ray photon is about 1,000,000 electron volt, a big difference in the energy. So you must have a rough idea on electromagnetic waves, their relative wavelength to frequencies and energy values. Visible light consists of over 3,000 different frequencies, and each frequency corresponds to a color. So how many colors are there in our visible light? There are over 3,000 different colors. Well, the perceived colors, very often people talk about 7 colors, the rainbow colors. They are the perceived color, like red, orange, yellow, green, cyan, blue, and violet are actually combinations of many hundreds of wavelengths. Now, for example, red is a combination of wavelength from 625 to 740 nanometer. Now, blue color that we normally see as blue is a combination of wavelength that range from 435 to 500 nanometer. So it's a combination of about 65 different wavelengths. Alright, let's do an example. Find the wavelength for a radio wave of frequency 1000 kilohertz, a radio wave of frequency 100 megahertz. It's a very simple problem because you know that the speed of all electromagnetic waves is 3 times 10 to the 8 meter per second. And we also know that speed is related to frequency and wavelength as c equal to f lambda. So to find the wavelength, we solve for lambda here. Lambda equal to c over f. So in the first case, it will be c divided by 1000 kilohertz is 10 to the power of 6 hertz, and that is 300 meter, the wavelength of that wave. In the second case, the frequency is 100 megahertz. Well, 100 megahertz is 10 to the power of 8 hertz, and that wave has the length of 3 meter. As the frequency increases, the wavelength becomes shorter and shorter. Second, what is the frequency of a 1.2 centimeter microwave? Well, again, solve for frequency and use the given values, and that is 1.56 times 10 to the 10 hertz. Next, we will briefly discuss energy and momentum in an electromagnetic wave. These waves carry energy with them. The propagation of electric and magnetic fields results in the propagation of energy. Now, this means that electric and magnetic fields carry energy. Now, the electric energy density U sub E of the electric field E and the magnetic energy density U sub B of the magnetic field B are given by the expressions. We actually discussed them briefly before, if you recall. And these expressions are U sub E, which is the electric field, electric energy density, is 1/2 epsilon naught E squared. And a similar expression for magnetic energy, U sub B, that is the magnetic energy density, is B squared divided by 2 mu 0. I think we discussed these in our last lesson. Now, since E equal to CB, remember that? We can actually modify these equations. Suppose we replace our B by E divided by C here. Can you do that? Replace this B by E divided by C. What will that become? UB become E squared epsilon naught mu 0 over 2 mu 0. Is that right? Well, did you see how that was obtained? Well, we replaced B by E over C, and our C is 1 over square root mu 0 epsilon naught. I want you to do that on your own and see whether you come to this. You can see UB therefore also is 1/2 E0 epsilon naught E squared. That means if you replace B using E equal to CB by E over C, you will see UE and UB really have the same magnitude. So, the energy density is the same for both E and B. That's what we just showed. The total energy density, therefore, of the electromagnetic wave U is the sum of the two, UE plus UB. That is 1/2 epsilon naught E squared plus 1/2 epsilon naught E squared is epsilon naught E squared. And you can write this also as B squared over mu 0. Epsilon naught E squared and B squared over mu 0 are both the same, using the relation E equal to C times B. And of course C equal to square root of mu 0 times epsilon naught. Okay. Now the average energy density can be obtained by replacing E and B by their RMS values. So if this is the energy density for an electromagnetic wave, EB divided by mu 0 C, what is the average energy density? It will be E RMS times B RMS over mu 0 C. Now this average energy is a measure of the momentum P carried by the wave per unit time per unit area. Now that's an important concept. Alright, so the average energy E RMS B RMS over mu 0 C. Now what is the meaning of intensity of a radiation? We talked about in connection with our discussion on waves, intensity. Now, if there is a radiation that is emitted, for example, I'm standing in front of a projector and the light that is falling on me is from the lamp of the projector. That's why you see my shadow on the board. Now, what is the measure of the intensity of that radiation? Well, in order to define the intensity at a particular point, what we do is we keep a unit area where we want to find the intensity. It is the amount of power crossing at right angles to a unit area is what we call intensity. So intensity is a measure of the power crossing unit area at that particular place. Now, if I move this unit area away, the amount of power crossing that unit area will be now less. That means as you move away from the source, the intensity will become less and less. Alright, so the intensity I of the wave is defined as the product of wave speed and the average energy density. Well, having known what intensity is, we can make use of that definition. In other words, intensity I is the product of the wave speed C and the average energy density. So I can now write it as C times the average energy density is E RMS B RMS divided by mu 0 C, and that will be E RMS B RMS divided by mu 0 because the C's will disappear. Now, the intensity divided by C is the force per unit area. What is force per unit area called? Force per unit area is called the pressure, and therefore the radiation pressure, whenever a radiation falls on a surface, there's a radiation pressure. And how do you calculate the radiation pressure? It is the intensity divided by C. I divided by C is radiation pressure. So P sub R, the radiation pressure, is intensity I divided by C, the wave speed. And that is equal to U is E RMS B RMS divided by mu 0 C. In other words, this is I. If you divide that by C, you get mu 0 C on the denominator. So that is an expression for the radiation pressure. You can also write it as E max squared divided by 2 mu 0 C squared. Now, how did that come about? Can you picture that? Well, E equal to CB. So B equal to E over C. And that is where the E squared comes in and the C goes to become C squared. Is that right? Replace this B by E over C and you get that equation. So the radiation pressure is E max squared divided by 2 mu 0 C squared. And that can also be written as B max squared over 2 mu 0. How? By replacing E equal to CB. Alright, let's do a small problem. A 50-watt electric light bulb emits spherical electromagnetic waves in all directions. Find the intensity of the waves. Well, this is where the original definition of intensity is going to help. What is intensity definition? It is the power crossing unit area at that point. That's how we're going to calculate that intensity. The radiation pressure and the electric and magnetic fields at distances 3 meters from the bulb. Well, in fact, I'm standing about 3 meters from the bulb, and this problem is very much applicable in my case. What is the radiation pressure on my face? What are the values of electric and magnetic fields where I'm standing? Well, the intensity I at a point is a measure of the power per unit area at that point. Is that right? So, I equal to 50 watt divided by 4 pi r squared. In fact, that's the bulb about 3 meters from there. That's the distance r, and you can see if I construct a sphere of radius r, the total power that is going out of that sphere will be, that's the total power. If you divide by 4 pi r squared, which is the area of that sphere, that will give you the power per unit area. I hope you understand that. If I have the bulb, lighted bulb here, if you take a surface of radius r around it, the area of that surface will be 4 pi r squared. So if you want to find the intensity at any point, divide the total power, which is the 50 watt given to us, by the total area, which is 4 pi r squared. So intensity I is power divided by the area, and that will be 0.442 watt per meter squared. Once you know the intensity, we can find the radiation pressure. What's the definition of radiation pressure? Radiation pressure is intensity divided by C. So P sub r is I divided by C, and we know those values. That gives you 1.47 times 10 to the negative 9 Pascal is the radiation power. Well, we now need to find the electric and magnetic fields where R equal to 3 meter. And for that we go and select this equation. We have obtained several equations for the radiation pressure in terms of electric field and in terms of magnetic field. So we are now going to use the equation in terms of electric field. PR is E0 squared divided by 2 mu 0 C squared. And we know all these values. Therefore, E max, well, E max is the same as E0. But E0 squared is 2 PR mu 0 C squared. Therefore, E max is the square root of that quantity. And use all those values. We just calculated the radiation pressure. We know mu 0 and we have C squared. That gives you E max, the maximum electric field is 18.2 volts per meter. Now, in the same way, you can calculate the magnetic field. I think I'm going to leave that for you and go to another problem. The amplitude of an electromagnetic wave is E max equal to 140 volts per meter. Find E RMS, B RMS, the intensity I, and the radiation pressure P sub R. Well, they're all direct applications of the formula we have. E RMS is E max divided by square root of 2, and we have E max. Therefore, the RMS value of that voltage is, of that field is 99 volts per meter. Now, B RMS is E RMS divided by C. Is that right? Yes, because E equal to CB. So since we have E RMS, B RMS can be calculated as 0.33 micro Tesla. Now, radiation pressure, the intensity is E RMS, B RMS divided by mu 0, and we have both these values, and that gives you the intensity as 26 watt per square meter. And what else do we need? The radiation pressure. Well, we have the radiation pressure P sub R equal to I over C. We have I, and we know C. That is 8.7 times 10 to the negative 8 Pascal. Well, simple problems, but you must be able to recall all these equations. Well, and that is the end of our discussion on electromagnetism. And I think in this unit I'm going to include a lesson on light, because it's very appropriate. After we discuss electromagnetic waves, light is a form of electromagnetic waves, so we spend at least one lesson talking about electromagnetic waves.